what to do when you put any graph that we've done already inside absolute value bars. So far, the only absolute value graph we did back in our very first chapter was transformations. And it looked like that. And you memorized what that graph looked like, and you did it with the table of values. And then you could do transformation, move it left, right, up, and down. But what we're going to do is when you have any function in the inside, we're going to, instead of having all those graphs memorized, we're going to start off with the technique of graphing the inside. So if I just graph the inside of y equals x, do you see that you would get this straight line? Like that. That's y equals x. I'll label it here. This is y equals x. And this is the absolute value of x. And you know that the absolute value bars, what do? If you have a negative number, they make it positive. Because what the function is trying to say is, how far is a number away from 0? -2, how many units is -2 away from 0? It's 2 units away. So it changes all the negative numbers to positive. But how far is the number 3 away from 0? It's 3 units away. So positive numbers stay the same. Graphically, what does that happen? On your graph, where are our y values negative? Can you see that that's this section of the graph where the y values are negative? And if you want to make something negative into positive, one way that you could do that is to multiply by a -1. And if I took this part and multiplied it by a -1, that's a vertical reflection. That just takes whatever is below the x-axis and flips it up. And that's going to be our technique that we're going to do in order to graph the absolute value of any function. Graph the inside first. Then whatever, like if I graph the inside here, that would be y equals x. That's the blue graph. Then wherever your graph's y values are negative, in other words, wherever the graph is below the x-axis, then your y values would be negative. The absolute value would make those y values positive. So you just take the part of the graph that's below the x-axis and flip it up. And that's as easy as it gets. So if we had this question, we could do it with transformations, because we're going to want to graph, oops, that's a little yellow. We're going to want to graph this. You could do this with transformations. You're going to have a horizontal compression and a horizontal translation, or we could do it with our new method. I'm going to do the new method first, then I'm going to do your old method, and you can decide which one you like better. Okay? The new method says, first, draw the inside. Well, 2x plus 3, that would have a y-intercept of 3, a slope of 2, and when drawing graphs, label your x-intercepts and y-intercepts. So my x-intercept here, but y equal to 0 would be -3/2. You draw your inside graph first. Then whatever's positive is going to stay the same. So we're still going to have on our absolute value, we're still going to have that point. It's going to be really important to label your x-intercept. So I'm going to label -3/2, 0, because that's the place where it's positive. And everywhere where it was negative, you're going to reflect it up. So we get the same v-graph that you would have got by doing transformations. Okay? If you did this with transformations, you have to be careful, because can you see that plus 3? You might think, oh, that's going to move it 3 to the left. But we look at our graph, it didn't look like it moved 3 to the left. It looked like it moved 1.5 to the left. Why? Because if you have, oops, I'll go back to black. If you have a horizontal compression and a horizontal translation, you have to write it in factored form. So if we did this, with transformations, we would have to do a horizontal compression by a half and then move it negative 1.5 or 1.5 units to the left. I think drawing the inside graph and then just flipping the bottom part up, I actually think that's a little bit easier in this situation. Because you don't have to worry about the factoring part. It wasn't hard to find the x-intercept and find out where the graph changes. But you could have done it with transformations as well. So what does this mean? We can use this technique to graph anything. So here's a graph from chapter 1, polynomial graph. It's already in factored form. Each of those factors has a multiplicity of 1. So in factored form, you'd be able to say that I have an x-intercept here at minus 3, 0, 1 at 0, 0, and this one at 2, 0. So right beside this, I'm going to graph those important points. When you do the absolute value, they will not change. Because the absolute value will just take the parts where the graph is negative and flip it up. So between negative 3 and 0, that part would stay the same. Because the y values were positive, the absolute value won't make a difference. After 2, this part of my graph will stay the same. But where my y values were negative, you have to do a vertical reflection. So this part will flip up to look like that. And this part left of negative 3 will flip up. And this is the absolute value graph. So I'm going to do one more example of how sometimes on the exam they'll combine all of these new functions, okay, with the old transformation rules. So this could be, right, we've sort of learned 3 special functions. We did one in chapter 2. You learned how to square root any graph. We have now learned how to do 1 over any graph and also the absolute value of any graph. And they can combine this with chapter 3. So I'll give you an example of what that could look like. You had one on your last take-home quiz. Maybe 2 take-home quizzes before, where I gave you that square root graph and then square root of f of x, and you had to like move it around. I don't know if you remember that question. But if I say given f of x equals x squared minus 4, graph y equals the negative absolute value of f of x plus 3. Whew. So let's think about what everything that's here. F of x equals x squared minus 4. That's a parabola moved down 4 units. You could graph that. Here, I see the absolute value of f of x. You could graph that. That would just be that parabola that's moved down 4 with the bottom part flipped up. And if you had a negative in front and a 3 afterwards, you could go to transformations. A negative in front of a graph, that takes the entire graph and does a vertical reflection. A plus 3 after something, that takes the entire graph and moves it up 3 units. So it's a little bit of problem solving here because we're connecting 2 or 3 units together. So first of all, just to visualize this. F of x, x squared minus 4. I'm going to graph that. Label all x-intercepts and y-intercepts. That's y equals x squared minus 4. I'm going to graph or maybe I'm going to, since we had labeled it as f of x, I'm going to just change this here and write f of x, because in my second graph here, I'm going to graph the absolute value of f of x. That would just take what was below and flip it up. And now I'm going to think about graphing what would happen if I did all of this. The negative would be a vertical reflection. And the plus 3 would be a vertical translation 3 units up. Could you do that all at once? Could you take this, flip it down, and shift it up 3? If you could, you can draw the graph right away. If you need to do it in steps, draw it flip down first, then move it up 3. So my final graph is going to look like this. I'm going to start with this point, 0, 4. Can you see that if you flipped it down, it would go all the way down to minus 4, but then when you shifted up 3 units, it's going to be at 0, -1. If I take this point, 2, 0, flipping it down is still going to be 2, 0, but when I shift it up, I'm going to get 2, 3. I'm also going to get -2, 3. There's my final graph. And it combines some of our transformations unit with this unit, absolute value graph. So sometimes you're going to get transformations with some of your special functions.